Hello, everyone. Good morning, good afternoon, and good evening. We hope all of you are doing great and staying safe. On behalf of Arab Oil and Gas Academy, I would like to welcome you all to the last webinar of the Natural Gas Engineering Internship. My name is Numan Mana. I'm a petroleum engineer working as a field engineer with Halliburton, Iraq, and I will be your moderator for today's session. Before we begin, let me remind you to kindly leave your questions in the Q&A section down below and kindly finish your quizzes before the deadline. Now, without any further delay, please help me to welcome our special guest speaker, Dr. Bob Chase, who will be giving a lecture on the gas well deliverability. Dr. Robert W. Chase holds bachelor, master, and PhD degrees in petroleum and natural gas engineering from Penn State and is a registered professional engineer in Ohio. He is a member of the Society of Petroleum Engineers, the Ohio Society of Professional Engineers, and the Southeast Ohio Oil and Gas Association. He served as a professor and chair of the Department of Petroleum Engineering and Geology at Marietta from 1978 to 2015. Prior to coming to Marietta, he served as an assistant professor of petroleum engineering at West Virginia University. He worked previously for Halliburton Services, Gulf Research and Development Company, and the Department of Energy, and has consulted for numerous companies. He currently serves on the board of directors of Settlers Bank of in Marietta, Ohio, and on the board of directors of Producers Service Corporation in Zanesville, Ohio. He was appointed by Governor Ted Strickland to serve a 5-year term on the Ohio Oil and Gas Commission in 2008. Dr. Chase, it's a pleasure having you today with us, and the mic is yours.
Thank you, Luma, for that nice introduction. And I want to say to everyone that I'm happy to be back in the Middle East today, even though I'm not really there. I have been over there many times, visited Egypt back in 1995, and have been to many other countries over there over the last several years. Today I'm going to be talking about gas well deliverability testing, but I wanted to start out and just kind of demonstrate how much we have more in common with each other than you might imagine. I just recently had my DNA analyzed by Ancestry.com, and I think you'll all find this interesting if you can take a look at me. And obviously, I'm very fair-skinned, and Ancestry.com provided an ancestry or a DNA analysis for me. And they found that my DNA was primarily Germanic Europe, a little bit, 18% from England and Northwestern Europe, 7% Irish in my background, 5% Norwegian, so I have a little Viking influence. Interestingly enough, 2% Nigerian, and this next one is what brings us all together. In my background, somewhere, someone along the trade routes back in ancient times must have visited Germanic Europe, and consequently, I have 1% Middle East in my background. So I say to all of you, salam alaikum, and hope you all have a great day and enjoy the presentation. Okay, so let's dispense with humorous information and talk about well testing. You're probably all familiar with pressure transient analysis, and I want to distinguish that from deliverability testing because pressure transient analysis we use primarily to determine the parameters you see on the screen: permeability, skin factor, flow efficiency, fracture half length, average reservoir pressure, radius of investigation, etc. Deliverability testing, on the other hand, is what we use to predict the inflow performance of gas wells. Now, you may be more familiar with predicting inflow performance of oil wells. I'm sure many of you have studied about predicting IPRs for oil wells, using Vogel's method. And what you should remember from that process is that to predict the inflow performance for an oil well, you really only need one flow test, a stabilized value of flow rate until your bottom hole pressure stabilizes at a PWF. And then you also need your average reservoir pressure. And with that basic information, you're able to predict the inflow performance of an oil well. On the other hand, gas wells are very different. And the biggest difference between working with gas and working with oil, of course, is turbulence. Turbulence is a big factor in the well testing process. And because of turbulence or non-Darcy flow, we're not able to predict the inflow performance of a gas well using just one flow test. And that's what we're going to focus on and learn about today. So let's talk a little bit about the goals of deliverability testing. The first goal is that we want to be able to predict the inflow performance of our gas well. A term that we use a lot in the United States and in Canada in particular is a term called absolute open flow, or the AOF, of our gas well. The absolute open flow of a gas well is the flow rate that a well will produce at against a zero sand face back pressure. In other words, a flowing bottom hole pressure of zero. So when you relate this type of testing to oil well testing, we're really talking about our maximum gas flow rate, QG max. And that would be the equivalent of our maximum oil flow rate in an oil inflow performance test. In addition to predicting the current inflow performance curve for a gas well, we would also like to be able to predict future IPRs. And as you all probably are familiar with the process of nodal analysis, we like to be able to predict the future as well as the current. So future IPR curves are very important, and we'll see how we can do that. Okay, a little bit on the history of deliverability testing. The groundwork for predicting gas well deliverability was done by two researchers with the United States Bureau of Mines. Now, interestingly enough, in the early days of the oil industry in the United States, their primary regulatory body that oversaw what was going on in the oil and gas industry was the United States Bureau of Mines. It later became, I believe, the Department of Interior. But two researchers by the name of Pearson Rollins in 1929 did early work. And then Rollins and another gentleman by the name of Shale in 1936 published a monograph called Back Pressure Data on Natural Gas Wells. And in that publication, they laid the groundwork for what we call 4-point testing, deliverability testing. Now, the wells that Rollins and Shale studied and worked on were all very good gas wells and produced at high rates. The rock had good permeability. In the 1950s, 1955, a gentleman by the name of Cullender published another landmark publication, the Isochronal Performance Method of Determining the Flow Characteristics of Gas Wells. He looked at wells that did not stabilize as quickly as the wells Rollins and Shale looked at. Further research continued in this area because a lot of the wells in the United States and Canada that we produce are low permeability wells. And in 1959, Marvin Katz, very famous engineer from the University of Michigan, continued his work and published a modification of the isochronal method that was developed by Cullender. And we call this method the modified isochronal or modified Isochronal Test method. And we're going to learn about all three of these different methods here in just a few minutes. Okay, so as I mentioned, under the category of gas well deliverability testing, because of turbulence and non-Darcy flow, it is impossible to characterize the inflow performance of a gas well with just one flow test. We have to use 4 flow rates, and I'll explain why we use 4 flow rates and not 3 and not 2 in just a little bit. But in the method by Rollins and Shellhart, they established the fact that you could take a well at initial reservoir conditions, PI or PR bar, and flow that well at 4 different flow rates, each one to stabilization. In other words, to reach pseudo steady state flow with 4 different flow rates 4 times. Cullender modified that process for wells that had lower permeability, and it took longer to stabilize. And he showed that if you could flow your well at 4 flow rates for a fixed period of time, delta T, and then allow your reservoir to build back up to original reservoir pressure in between your flow rates, and then maintain just your last flow rate until stabilization, you could predict the inflow performance of your gas well. That was further modified by Katz, as I mentioned, and he developed the modified isochronal test, where flow rates are maintained for fixed period of time, delta T, and the buildups in between are maintained for the same exact delta T as the flow period. And then finally, the last rate is flowed to stabilization. And we'll look at some examples of these 3 different methods in just a few minutes here. Now, again, I go back and contrast this to oil wells where we can characterize inflow performance with just one flow test. Some folks have tried to characterize gas well deliverability with just single flow tests, but you have to make some serious assumptions, and single point tests really are not the best way to determine accurately your well's inflow performance. All right, so let's talk about the first of the 3 methods, primary methods for determining gas well deliverability. Monograph 7, as I mentioned, was developed by Rollins and Shellhart in 1936. And they came up with an empirical equation that we see on the screen here that says Q is equal to a constant C, which we call the performance flow coefficient, times the quantity PR bar squared, that's your average reservoir pressure, minus the flowing bottom hole pressure squared, and that PWF is the flowing bottom hole pressure at stabilization or pseudo steady state flow value of PWF, raised to an exponent n. And interestingly enough, n must be in the range between 0.5 and 1. If your exponent n calculates to be 1, it means you have completely laminar flow. And any of you who have studied natural gas engineering know that rarely do we have laminar flow in gas wells. If we have completely turbulent flow, then n would equal 0.5. If n is greater than 1 or less than 0.5, then you really need to consider retesting your well because something was probably wrong in that process that you did when you tested the well. Okay, so monograph 7 outlined what we call the 4-point test procedure for determining gas well deliverability or inflow performance. The 4-point test or flow, it's also called the flow after flow test. The procedure we use is that we start with our well shut in. We do that so that we could obtain the bottom hole average reservoir pressure PR bar. And I will mention that you really must use bottom hole pressures when you're doing this type of test. Using surface pressures or casing head or tubing head pressures is not recommended, because if you replace the tubing in your well for any reason and you put a new diameter tubing in, it will not reflect bottom hole conditions. So you really do need the bottom hole pressure conditions. So after we've shut in our well and we've recorded our average reservoir pressure PR bar, we flow our well at a rate Q1, and we maintain that flow rate until the bottom hole pressure stabilizes at PWF1. We signify the one designates just the first flow rate. We repeat step 2 for increasing flow rates, Q2, Q3, and Q4. And in that process, as you can see on this graph, in the top portion of the graph, we see the 4 flow rates maintained to stabilization. And in the bottom graph, we see how bottom hole pressure has declined as a function of time, stabilized at PWF1 for Q1, et cetera, for PWF4. Very often at the end of a test, we allow the well to build back up to initial reservoir pressure PR bar. Now, this data, the flow rates, and we always use the endpoint of those flow graphs. Where you see Q1, you notice that it has declined a little bit with time and then stabilized. So we use to stabilize Q1, not an average during that flow period. And we use the PWF 1s, 2s, 3s, and 4s in order to make a plot like we see on this next graph. Now, normally we plot our data on log paper. So you see on the y-axis, we have the log of delta P squared, where that delta P squared is your PR bar squared minus PWF squared, like you see in the equation on the right-hand side of this plot. And we plot that versus flow rate on the x-axis on a log scale also. You see here that we have 4 data points, and we're able to draw a straight line through that graph. And the slope of that line is equal to 1 over n. Now, if you look at the equation on the right-hand side of this graph, you see that that exponent n appears in the equation, and therefore n is equal to 1 over the slope of that line. So you need to be able to measure the slope on log paper, and I'm sure you all have done that at some point in your education. So if you take when you're calculating your slope, if you choose 2 points exactly 1 cycle apart on your y-axis, come into your straight line and read off the flow rates associated with those 2 points exactly 1 log cycle apart on the y-axis, you're able to determine your n value equal to the log of Q2, your second flow rate, over Q1, as you see over on the right-hand side. To calculate your flow coefficient, your performance coefficient C, we can choose any point along that straight line, call it QSC, and the coordinate, the delta P squared coordinate of that same point, PR bar squared minus PWF squared from the y-axis, and raise that to the nth power, where n is the value you just found from the log of Q2 over Q1, and calculate your value of the flow performance coefficient C. Once you have C and N, and if you know your initial reservoir pressure squared, which you now do from your test, you can plug in a series of PWF values in between 0 and your initial reservoir pressure, calculate values of Q, and then plot an IPR curve using that equation. So let's talk a little bit. We'll go back a second. We want to talk about the mathematical justification for being able to plot this data as a straight line on log-log paper, reflecting the equation that we see on the right-hand side here, the equation of stabilized deliverability. Q is equal to C times your delta P squareds to the nth power. So in their publication in 1937, Rollins and Shellhart proposed the equation that we see here and we just talked about. And if we take the log of both sides of the equation, we have the log of Q is equal to the log of C plus your N times the log of delta P squared. That's just a matter of taking the log of both sides and using your mathematics to do that. And in 1937, Rollins and Shellhart rearranged that equation, and we see you have the log of the delta P squared is equal to 1 over N log Q minus 1 over N to the log of C. 1 over N log C is just a constant, but you can see from this equation that plotting PR bar squared minus PWF squared as your Y value on a log scale versus flow rate Q on the x-axis, you have the equation of a straight line where 1 over N is the slope of that straight line, just like we saw on that last slide. Okay, so here we just repeat the same thing. The equation says plot that versus delta P squared versus Q on log-log paper. You get a slope equal to 1 over N, and then you find C by rearranging the equation as we showed on the last slide. Now, we've come a long way since 1937. There were no computers in 1937. There were slide rules. And that's how Rollins and Shellhart did all their work. In fact, that's how I did all my work as an undergraduate at Penn State back when I started school in the 1960s. You all have computers. We can do most of this stuff on our phones these days. But I just want to point out that today we don't need to stick to the old ways. If we look at equation 2 up above, equation 2 says if you plot flow rate on your y-axis versus PR bar squared minus PWF squared on your x-axis, you have a slope of N directly, and you're going to be able to get your stabilized performance coefficient off the graph as well. And if you do this in Excel, I'll show a little example here in a minute, and you use the power law fitting function in Excel, you get this information directly. So we'll talk about the conventional way to do it, the old way, what people have been using for the last 70 years, 80 years, and what we can now do with a simple computer program. Okay, so here's the justification. We're going to make log-log deliverability plots. The old way is to plot delta P squared on the y-axis and Q on the x-axis. The better way to do it is plot Q on the y-axis, delta P squared on the x-axis. Okay, so here's a little example that is one of my favorites I used to use when I taught petroleum engineering and natural gas engineering, which I did for 39 years. We have a well that has an average reservoir pressure, bottom hole pressure, of 201 psi. Now, is that a good well or a bad well? You have to ask yourself. I'd always ask my students that. And the answer was overwhelmingly, why would anybody produce a well that has just a bottom hole pressure of 200 pounds? Well, this well was tested using conventional 4-point test theories, and it was flowed at 4 different flow rates, and the bottom hole pressure stabilized at the 4 values of PWF that you see there, 196 psia through 190 psia. So I ask you what your initial reactions to this data are. And I would ask you, is this a good well or a bad well? Most people would say this is a bad well. It only has 201 pounds pressure. And when you're flowing your well, you're not getting much of a drawdown. But we need to look at the rest of the data. We need to see what the flow rates were. And in this case, the bottom hole pressure was 201 pounds, and the well stabilized flowing at a rate of 2.7 million cubic feet of gas a day, or 2,730 MCF per day, stabilized at 196 psi. And it turns out it stabilized very rapidly because it turns out this is a reef structure up in Canada that has very high permeability and very high deliverability. So even though the bottom hole pressure is low, it turns out this well turns out to be a very good well. And if you own this well, if you were a capitalist living in Canada instead of working in the Middle East, you'd be very happy to have this well or the royalties from it because it's a very good producing well. So, okay, so we want to analyze this data. We take our average reservoir pressure, 201 squared minus 196 psi squared. That gives us a delta P squared value. We plot that versus the flow rate, and we get a graph that looks like this. From this plot, we want to determine our N and C values. But before we do that, I just want to mention why we do a 4-point test and not a 1-point test. Obviously, if you have a 1-point test, you have no idea where to put a straight line through 1 point, could go in any direction. If you look at any 2 points on this graph and you just float at 2 points, you can see that you could get one straight line that is much lower than the one that I show in the picture. If I use the middle 2 points, I'd get a different straight line. If I use the second point from the bottom and the top point, I'd get a different straight line. If I use 3 points, I'd end up having to use the least squares method to fit a straight line through the data. And by having 4 points, we can see here that it looks like 3 points are pretty good points and 1 point is an outlier. So we could discard that point from our data and use what appear to be 3 good points to get our straight line. Okay, analyzing this data, we found this is the data that was used to prepare that graph. The results at the bottom show that our graph had a slope of 1.0815, which you get as the exponent for your x value in this particular case. And 1 over that slope gives us our n value of 0.92. And if you remember, we said that n has to be between 0.5 and 1. The closer it is to 1, the more laminar flow is. And in this case, the well, the reef structure had a high permeability and flow was more laminar than turbulent. We calculate our C value, 2.42 MSCF per day to PSIA squared. And we find our flow rate, our maximum flow rate against the 0 sand face back pressure from our deliverability equation of 44,000 MCF per day, or 44 million cubic feet of gas a day. So we see here your initial reaction, was this a bad well? You probably thought yes, but the well's capable of producing at a very high rate, 44 million cubic feet of gas a day when it's wide open, and you have a theoretical value bottom hole pressure of 0. Now, same data plotted in modern fashion, 2012 fashion, Q as your Y value and delta P squared as your X value. And you look at the equation using the power law fitting formula on Excel, and you'll see that you get an exponent for x of 0.9279 and a C value 2.4165. Compare that back here, you see the N is 0.9246 and C is 2.42. So plotting it in the unconventional way, we get the results we want directly for C and N using Excel. Okay, now let's talk a little bit about this thing called time to stabilization, because anytime you're doing a 4-point test, all 4 of your flow rates have to be maintained to stabilization. The time to stabilization equation comes from the solution of the diffusivity equation using the exponential integral function. And this is the Canadian version of time to stabilization, or pseudo steady state flow. And it says time to stabilization equals 1,000 times porosity, viscosity, your external drainage radius squared, divided by permeability, and your well's average reservoir pressure. The actual equation is 948 phi mu RE squared K PR, but the Canadians like to round things off a little bit, and they use 1,000, and I took this from a Canadian well testing monograph. In John Lee's book, which a lot of you probably use in your classes, 948 would be the exact constant to use. Okay, so our goal is to find the equation of stabilized deliverability using the method that we just talked about. And the time to stabilization is very important. If your well stabilizes quickly, and you can estimate that time using this equation, then there's no problem. But if you're dealing with wells like I deal with here in the United States, we're producing gas, a lot of natural gas from shale, and the permeability of shale might be 1,000th of a millidarcy. Time to stabilization could be very long. And let's look at an example of that. We want to calculate time to stabilization for a reservoir that has an average pressure of 3,000 pounds, gas viscosity of 0.02 centipoise. We have a radius of drainage for this well of 1,000 feet. It's a 200-foot thick formation. Porosity is 10%. And we're going to look at 2 cases, a permeability of 100 millidarcies and a permeability of a 1,000th of a millidarcy. And when we do these calculations, we find for the well that has a 100 millidarcy permeability, K being 100 in the denominator of this equation, it only takes about 7 hours for this well to stabilize at a given flow rate. If we use a permeability of 1,000th of a millidarcy, we see that time to stabilization is 606, almost 700,000 hours. Now, if you're working in Ohio, where I live, and your boss says, go out and do a stabilized well test on a shale well and make sure it's stabilized, I say, I'll be back in about 100 years, because it's going to take me 700,000 hours to achieve stabilization. So that type of test is not, a 4-point test is certainly not practical on a shale well where that time to stabilization is so large. So when you're designing a test, and we're not going to talk about well test design today, but you want to make sure that one of the first things you do is you estimate time to stabilization, so you can determine whether you should run a conventional test or the test we'll talk about next, the isochronal test. Now, in this particular method, this is better suited for testing a well that has a lower permeability and stabilization times are greater than maybe 20 hours. You don't want to have to stay out there longer than about 20 hours to get stabilization. So in this case, we flow our well at a constant rate until our flowing hot bottom hole pressure stabilizes. We do this to ensure that the effective drainage radius is equal to 0.472 RE. That's basically what we're saying here, is that if we want to achieve stabilized flow or pseudo steady state flow in a reservoir, we have to maintain it until that particular radius of drainage is reached, and our pressure transient we've created in the reservoir has reached the outer boundary of our reservoir R sub E. All right. In 1955, Cullender talked about this, and he said that radius of drainage was a function of dimensionless time and not flow rate. And the dimensionless time equation is related to the one that I showed you before, the time to stabilization. You might have noticed, if I asked you the question, will gas wells stabilize at a flow rate of 1,000,000 cubic feet a day, slower than flowing your well at a rate of 10 million cubic feet of gas a day, you might think the well would stabilize faster at one rate or the other. But time to stabilization, as we saw in the equation just a few slides ago, is not a function of flow rate. Flow rate has nothing to do with time to stabilization. Porosity, viscosity, external drainage radius, permeability, average reservoir pressure, or total compressibility, those are the terms that affect time to stabilization and not flow rate. So you can choose any rates in your testing and still achieve stabilization at approximately the same time. Okay, an equation from well testing that, if you've looked at John Lee's book, this is a very common one you see in pressure transient testing. Your radius of drainage or radius of investigation in a well test is equal to permeability times the time you've flowed your well, divided by 948, or rounded off to 1,000 like the Canadians do, times phi mu CT. For gas wells, CT can be replaced by 1 over your average reservoir pressure. So this equation could also be expressed as KT PR bar divided by 948 phi mu raised to the 1/2 power to estimate the radius of drainage at any time for which you flow your well. So because the radius of drainage is not a function of flow rate and just a function of time, Cullender said, pick a delta T, say 10 hours, and flow your well at 4 different flow rates, each flow rate for the same period of time, say 10 hours. And that way your radius of drainage would be the same for each of those 4 flow rates. And you would essentially have the data you need to predict a transient curve or a transient straight line on a deliverability plot. He also said that in between those flow periods, you should shut your well in and build back up to your average reservoir pressure, PR bar. And then your last flow rate, you have to have at least one flow rate that has stabilized and your bottom hole pressure is stabilized to determine your true deliverability curve, the equation of stabilized deliverability. Okay, and again, I recommend that if your time to stabilization is about 20 hours or less, this method is an acceptable method to use, the isochronal method. So what does that look like graphically? Again, you flow your well at a rate Q1, your bottom hole pressure falls to a value of PWF1, but it has not stabilized. After a fixed period of time, say 10 hours, You shut that well in and you build it back up to your initial reservoir pressure PR bar. So you can see the increasing pressure back up to the pressure. And then we flow at a rate Q2. It doesn't stabilize. Pressure decreases to PWF2 and we shut in again. You repeat that 3 times, build back up to our average reservoir pressure, and then finally, our 4th flow rate, we're going to flow our extended rate until it truly stabilizes at some value of a stabilized flow. And we record our value of flowing bottom hole pressure at that stabilized rate. We call that PWF5. Now, because the radius of drainage is stabilized at those intervals, here we see a plot similar to the deliverability plot we saw just a few minutes ago for a 4-point test. But we see at a time of 1 hour, we're able to record pressures during our test, and we get a straight line reflecting our well's deliverability at a time of 1 hour. This is a transient deliverability curve. At T2, at a time of 2 hours, we can record flowing bottom hole pressures, record those points, and we get our data again following a straight line at time 2 or 2 hours. We do it again at 3 hours. We could do it at 10 hours. We could do it at 20 hours. We would find in every instance that these lines would have the same slope. And Colander saw this and realized that by doing this, he only needed to flow his well at one stabilized rate out here, Q4, which he did for 72 hours on this well. And he said, I know that the straight line through this point has to be parallel to the lines through the other points. Again, this is the plot of delta P squared versus flow rate. So all the lines have the same slope, but what we have to realize is that our C value will be different for each line. You remember the equation of stabilized deliverability is Q is equal to C times delta P squared to the nth power, and N is equal to 1 over the slope. So if the slopes are all the same, we know N never changes. But C is going to change for each of these values. And you notice that our curves are migrating from right to left, which means that our C value will be decreasing as we approach pseudo-steady state or stabilized conditions. And what we want is the stabilized C value. All right, moving on to the third method, the modified isochronal test that was developed by Katz. Katz was interested in being able to predict deliverability for low permeability wells. And he proposed a shortcut where he said, I'm okay if I can just approximate isochronal test behavior. I know it's not going to be as accurate, but what he said was, if I make my shut-in times equal to my flow times and still have 1 point to stabilization, I'll get a good estimate of my well's deliverability. So we see the similar plot like we've seen before. 4 flow rates flowed for equal periods of time, a delta T, say 10 hours, and then in between a shut-in period of 10 hours. And then in the last case, we can extend the flow rate until stabilization occurs and get a value of a stabilized Q and 1 value for flowing bottom hole pressure at stabilized condition. That would be our PWF5 value. And he did the same thing that Colander did. If he did a 10-hour transient time period test, he got 4 points that fell on a straight line, which allowed him to calculate his slope. He shifted a line of the same slope through a stabilized point, which gives him the stabilized curve, and he can then calculate the equation of stabilized deliverability. Okay, generating IPR curves, we said that's the ultimate goal, and we want to be able to do that. So in order to do that, we need several pieces of information to do that. If you know your well's current average reservoir pressure and you've tested your well and found your N and your C, then all you have to do is assume values of PWF in between 0 psi and your average reservoir pressure and calculate corresponding values of Q versus PWF. And that would allow you to calculate and predict your inflow performance curve, which is a plot of PWF versus Q, very similar to an oil well, the curve you generate using Vogel's method. And like we see down at the bottom here, flowing bottom hole pressure plotted on the left, flow rate on the x-axis. We see we get a curve here at showing an absolute open flow potential of 8.5 million cubic feet of gas a day. Now, the beauty of this method is that if you want to predict future well deliverability, all you have to do is assume future values for your average reservoir pressure. Let's say your average reservoir pressure is 1,500 pounds in the future. If you assume that your C and N values don't change, and they might a little bit over time, but you can assume they don't change, you just put your new average reservoir pressure in 1,500 pounds, and you can generate a new IPR curve that will be pretty much parallel to the one that you see in this graph. And you can generate a whole series of IPR curves down to your abandonment pressure, your final abandonment pressure for PI. Now, I'm throwing a lot at you, I realize, and I'm going to throw some more at you because there are multiple ways to analyze well test data, deliverability test data for gas wells. And I want to point out another effective way of doing it, and it's utilizing a method that you'll find has different names. In Canada, they talk about the Forsheimer equation. In a well testing book by some folks from Tulsa, their name escapes me right now, they talk about the Jones-Blount-Glaise method of analyzing deliverability test data. The Canadians talk about the laminar inertial turbulent flow equation. And in John Lee's book, he refers to it as Hoopert's equation. And that equation is the first one that we see at the top of this page that says your average reservoir pressure squared minus PWF squared is equal to a term A prime Q plus B prime Q squared, where your A term in that equation, or A prime term, reflects the laminar component of the equation, and the B prime term that you see having a capital D in it. That capital D is what we call the non-Darcy flow coefficient that reflects turbulence in a gas well. Therefore, that B prime term represents the turbulent flow term in the equation up above. So theoretically, if you know all of the components of A prime and B prime, you can calculate those two values, plug them into that top equation, and knowing your average reservoir pressure, you can substitute a series of PWF values in and solve for Q. You have to use the quadratic equation to do it, but you can solve for values of Q versus PWF and predict your gas well's inflow performance using that method. Most people prefer using pseudo pressures when working with gas wells, so we see a second form of that equation down below. using the psi term, psi of PR bar minus psi of PWF. Those are just pseudo pressure functions that you're probably familiar with or will be when you study the natural gas. But you see the same components, A and B, where A is a laminar term and B is a turbulent term. So the question is, how do we utilize these equations in predicting gas well deliverability? Well, all of the folks I mentioned, Jones, Blunt, Glaze in particular, Hooper, said if you take the equation A at the top of the page there, PR bar squared equal to A plus B in those terms, if you divide both sides of the equation by Q, you end up with the expression PR bar squared minus PWF squared over Q is equal to A plus BQ. Obviously, this is the equation of a straight line that says plot PR bar squared minus PWF squared over Q as your Y value and Q at standard conditions as your X value. And if you do that, you'll get the equation of a straight line where each of the 4 points that you see on this straight line are points from our deliverability test, the way we obtained our deliverability data before from an actual field test. The slope of the line B in this particular graph we see indicated, and the intercept at a value of Q equal to 0 is shown as 1.192. We calculate A and B, and from that, we now have the equation, the values of A and B that we use in that equation. Knowing our average reservoir pressure, we can assume values of PWF, calculate values of Q, and predict a well's inflow performance. Okay, so what Jones, Blunt, Glaze said is you prepare an LIT plot, and an LIT plot is simply a plot that looks like this. Delta P squared over Q equal to A plus BQ. Okay, you prepare that plot, you determine AT, your value of A, B being the slope of the equation, A being an intercept of the straight line. If you're using isochronal test data or modified isochronal test data, then you have to do something similar to what we saw on the previous plots for those procedures. You will have a transient straight line that you'll use to calculate your B value, and you'll have 1 point on a stabilized line, so you'll put a parallel line through that value of your pseudo steady state value, and you're able to get the stabilized A value, the A at pseudo steady state conditions. Okay, and an example of that is shown here. We have pressure squared plotted, pressure squared over Q on the y-axis versus Q on the x-axis. We have 4 points taken from transient data that we get, say a 10-hour flow period, and 1 point that has been stabilized. We get our slope from the straight line, and our intercept we get from the graph here. That would give us our A at pseudo steady state conditions, and we can use that to predict our deliverability. So down below here, we see the A from regression analysis, 4.92 times 10 to the minus 2 for our transient A and our slope B. Down below, we're able to find our pseudo steady state value of A. And from the data, we can calculate our stabilized deliverability. And that's Ahmed's phone ringing in the background, so you'll have to excuse us for that. Okay, I know I'm throwing a lot at you here at the very end. I'll be happy to make all these slides. Ahmed can make them available to you. And I'll put my email address up there again. If you have any questions, certainly can all email me. Again, here's another view of a typical IPR curve that we would get by knowing A and B and using our current average reservoir pressure here, it was 2,000 pounds. We can assume values of PWF and calculate flow rate values and generate the IPR curve here. And we can do the same for future IPR curves. Now, what if you can't flow your well to stabilization at all? What if you're dealing with a shale well? The shale well is a particularly tough issue to deal with. And I'm not going to say a lot about this, but I want you to be aware of two SPE papers that are excellent with regard to predicting gas well deliverability when you have no stabilized data. Fred Potman from the Colorado School of Mines published a paper in 1986, and it was based on a method of Brar and Aziz, who published a paper on using non-stabilized data to predict gas well deliverability. Both of these papers are excellent. They use the same information and procedures we were just using, the LIT equation or Hooper equation, and Potman showed that the value of A for transient flow is different than the value of A for pseudo steady state flow. And he equated them. And whether you're dealing with transient flow or pseudo steady state flow, the B value is a constant given by that equation. And Potman said that he equated the values of transient and pseudo steady state flow to come up with the term he called pseudo stabilization time. This is very similar to the time to stabilization equation we had earlier, where the constant was 948 phi mu c squared, re squared over k. Very similar term, as I note here. And Potman's procedure says run an isochronal test or a modified isochronal test, recording your flowing bottom hole pressure data versus flow rates at a series of times, say 1, 3, 5, 7 hours. Make plots on your regular graph paper, delta P squared over Q versus Q at each of those times. Solve for transient values of A and B for each of the lines that you get on your graph. And then he said, plot your transient value of A versus log of time, and you get a straight line of this form. If you substitute your value of pseudo stabilization time into that equation for T, knowing the slope of the line and the intercept, you're able to calculate your value for A at pseudo-stabilized flow, which is the value you want for predicting your well's inflow performance. You can use the average value of B for your lines at 1, 3, 5, and 7 hours. And from that average value of B and the APS that you get in step 4, you have the equation for stabilized deliverability that you can solve with the quadratic equation. Now, I realize that I've thrown a lot at you here in the last 5 minutes, and I did that on purpose because I want you to read. I want you, if you are doing any work on gas well testing, I think the paper by Brar and Aziz is an essential paper. And I think Potman's method for predicting gas well deliverability from unstabilized data, which is a modification of Brar and Aziz's paper, is an excellent one. And I would hope that if you have if you're dealing with those kinds of wells, lower permeability wells, that you'll consider reading those papers. and applying that methodology. All right, I'll close for now, and let's see if I can get out of this and go back to the very first slide, where you will find my email, chaser@marietta.edu, so that after this presentation's over and Luma, she might have a few questions for me, maybe not. If you have questions going forward, feel free to email me. So at this point, I want to thank you for attending the webinar, for listening in, and I hope.
Thank you, Dr. Well, for this awesome session. Thank you so much.
You're welcome.
So first question we received is, what are the main assumptions in a single point test?
If you're only going to use a single point, it's very dangerous. You have one point. Imagine that plot. Let's just say we'll get a curve up here. Okay. If you ignore the transient deliverability curves on this plot and you just have that one point, how would you know where to put a straight line through it? So some people will simply assume a value of a slope equal to 1. Now that assumes pure laminar flow, and we know that almost no gas wells have laminar flow. There's always some turbulence. Some people might just assume a value of n equal to 0.85, just because it's kind of an average value. Another thing that you could do is, if you've run tests on wells nearby, if you have good 4-point tests on neighboring wells, you could assume an n value for the neighboring wells and put a line of that slope through your single point. But there is always going to be some danger that your well is not similar to that offset well. So like I say, a 1-point test, you have to make too many assumptions. I've done a lot of work with, I've done a lot of research on single point testing, and came up with a method along with one of my favorite Middle Eastern students, Hassan Al-Kandari. He went on to get his PhD at Colorado School of Mines. And Hassan and I developed a method of analyzing data using a 1-point test, single point. And you can go into the SPE library and find that paper as well if you're interested in 1-point testing and read about it. I can tell you that the method has been built into several big nodal analysis programs that some of you may use. And if you look closely, if you just have 1 point, you're able to do that. But there's always danger when you're just using 1 point to analyze, to get a deliverability curve and to predict an inflow performance curve.
Okay, another question. Is it a good approach when we assume that the skin factor is a function of the flow rate in our interpretation?
Okay, is it a good assumption when we assume that the skin factor is a function of flow rate? In fact, that's exactly what the data, like we see in the graph that I have up there right now, that's actually reflecting the fact that your skin factor is being influenced by turbulence. You could take this same data and use a procedure that you'll find in any good well testing book, John Lee's or anyone else's, to determine the true, that we use to determine the true skin factor of a well. Some of you might be familiar with that. You calculate a skin factor for your well test at 4 different flow rates, plot that data versus flow rate, and extrapolate to a 0 flow rate and calculate the true skin factor of the well. And the slope of that particular curve would reflect the non-Darcy flow coefficient, D. So in fact, That's exactly what the N value in these plots, deliverability plots, reflects, is that um, there is skin. The skin is due to turbulence. Turbulence affects your data, which is why we can't just do a single point test. Now, I'll mention one other thing about oil wells, because I know a lot of you in the Middle East, you deal more with oil wells and you deal with some great wells over there. Oftentimes, we assume that our oil production is laminar in nature, and it isn't always. If you're dealing with high rate oil wells, you probably need to look at a procedure just like this. Any of these 4-point test procedures, they can be applied to oil wells to get a more accurate inflow performance curve.
Okay, that's pretty much it for the question. Wait, I think we have a last question. Is the flow in Vogel and Vitkovich is laminar or turbulent?
Could you repeat that again? It was a little, it broke
Is
up on
no
me.
problem. Is the flow in Vogel and Vitkovich is laminar or turbulent?
In which one? In this graph that I have up?
In Vogel and Vitkovich.
In general, you're going to find that flow is turbulent in gas wells. Very rarely do we see, sometimes we'll see an exponent n that is in the 0.9 range, reflecting that it is more laminar than it is turbulent. But very often we get n values that could be in the range of 0.5, 0.6, 0.7, indicating flow is more turbulent.
Okay, that's it for the questions. It was an honor to have you here today with us. Thank you again, Dr. Chase. Thank you very much.
Thank you, Luma, very much, and have a good day, everyone. Good evening.
Thank you very much. So, last reminder that this session is being recorded and will be posted on Biopetrol YouTube channel. And stay tuned for the other upcoming webinars by following Arab Oil and Gas Academy. See you again till next time. Take care, everybody.